All right, starting a quick, well, probably not quick, but we'll see how we go. Recording to talk through 2020 alternate sequence paper 2, question 8, regarding some refractive indexes of light. So question 8, 4 marks, is light of an unknown wavelength traveling through the air with a refractive index of 1 is incident upon a glass rectangular prism. The angles of incidence and refraction were measured, and the signs of these angles were graphed. We're given this graph right here with sine r on the y, sine I on the x. Refractive index of light is known to vary with the wavelength of light, as shown. So we got refractive index versus wavelength, and we got a bit of a curve, and determine the wavelength of light, the instant light used in this experiment. So we're going to start up here. We have to recognize that this is sine r on sine I, and we can actually, and we know from our formula sheet that basically sine I on sine r, sorry, I'm using a mouse to write this, so is equal to n2 on n1 on n1. In this case, basically our n1 is air, which is right here, right? So that means basically n1 is 1. So it's kind of like that doesn't exist, and we just basically kind of, our refractive index is n2 is what we're chasing. From this graph, we can see that our rise is sine r, our run is sine I, so we can actually figure out the gradient here of this, which is m is equal to basically kind of sine r on sine I. And if we do it correctly, we need to do y2 minus y1 divided by x2 minus x1. So I'm going to use these 2 points here. So I'm going to use this point up here. I'm just going to use this one down here just to kind of basically as the two extremities. There's no real perfect one here, but I can see that sitting right on the value, so you really have to kind of dive in and kind of get it. The thing is with the external ones is you do need to be as exact as you can be, within reason, of course. So let's take a look here. So we got m is equal to, so our y2 is up here. So y2, if we kind of trace this across, we got 0.52 essentially. So 0.52 is our first number, 0.52, and then we go down to the bottom point here, and our y value here is 0.125-ish. It's not really 1.3 because it's kind of not right in the middle, but we'll do 0.125. 125. Probably should only go to 2 decimal points to get my accuracy, my precision on these ones because of the way the graph is set up, but we'll see how this goes. We'll see if we get our numbers. Our x values. So going back here, look at our x values here. We got 0.78 is this line, and that's essentially pretty close to 0.79, so that's what I'm going to use, 0.79. Minus, and then come down here, and here we got 0.1, it's just past 0.19, so it's 0.195, just to 0.195. And again, probably should be using 3 decimal points, but I'm going to use it anyways. Going to pull out my trusty calculator, do the working out off screen, sorry. 0.52 minus 0.125, all divided by 0.79 minus 0.195, and we get a value of 0.6638. So equals 0.6638. Well, 39 essentially, sorry, 0.6639. Alrighty, so we get our m value there, but we know that basically kind of this is actually, because it's rise on run, basically this is actually going to be sine r on sine I. Sine r on sine I. So we need to kind of flip our fraction over. Right, and that's not going to work, so we've got to flip our fraction over, take the inverse. So therefore basically kind of our sine I on sine r, which equals to n2, is equal to the inverse of this. So we now say basically, well, n2 then equals 1 on this number, 0.6, oh, it's not working, 6639. And we can take the inverse 1 divided by that, and we get 1.506. 06 as our refractive index. The actual solutions, so basically the refractive index there is 1.511, so we're pretty darn close. and we'll see how that kind of changes down here. So we can actually now kind of head down to our graph. So this is our value we're going to be using for our graph number 2. And we're looking at the refractive index on the side here, and we're looking for basically 506. So if that's 510, it'll be 59, 58, 57, 56. And it looks like we probably won't have the value we're after because it's way down here. So if I look at the solutions actually show it as 1.511. Okay, so that's basically, so we have basically some sort of inaccuracy here. I wonder what would change if I actually made this instead of 0.13, and maybe it's probably closer to 19 than it is to 2. This is 0.1, sorry, that's down here. 0.125, yeah, probably 0.13. Let's see what happens. 0.52 minus 0.13 divided by 0.79 minus 0.19, and I get a value of 0.65 here. So that basically then equals 0.65, actually dead on. I take the inverse of that, and I get a value here of 1.538. Oh, and we can really see how that actually have changed here. So I just based it by 0.005 here, by 0.005 here. I've actually changed my refractive index massively. So you can see how much that the values actually decided. So if I go down here, 1.538 is actually way off the graph, way up here now. So again, that's no good to us. So there is going to be something in there that will basically we'll get the right number. I'm just going to, just for simplicity's sake, I'm going to say we're going to use the number from the solutions, which I'll change it to a different color again. Okay, so this number from the solutions, basically we get an N2 value of 1.511. All right, so now we can kind of take this number, look for 1.511, so 1.515, so it's a little bit less than that, so 0.510, cool, 1.511 would be kind of right here. So we're going to trace that all the way across to here, and then kind of head down from there to there. And we get basically a wavelength of light of about 550, that's 600, so that'd be, each of these is worth 5, I think, 60, 70, 80, yep, so that'd be 585 as our, so it'd be 85 millimeters. Sorry, nanometers, not millimeters, nanometers. Okay, so it is a paper 2 question, so we have to expect that there's going to be some little bit of niggly, and it's basically going to really be testing things. So that's where we really have to kind of get this precision in this section here to get our gradient, and then basically kind of use it correctly. The answer key does say that we can actually get anything between 570 and 600, so 550, 60, 70, so 570 and 600 is allowed, so anything in there, so that gives us a refractive index between right around here, so it gives us a refractive index allowed of basically about 1.51 to 1.53. Okay, somewhere in that range there, it basically kind of is allowed, the refractive index. And so even if you don't get the question correctly, so technically, basically, if we're going to mark this one, once again, let's go, keep going, all these fancy colors. I haven't used a pink yet. Let's use a pink. So understanding Snell's law and the gradient of the graph can be used. So that's basically kind of, you get 1 mark just for writing that or showing that with numbers. Provides pertinent mathematical operations correctly performed to determine the gradient. So you could technically, if you don't get the gradient correct here, you're not quite in the range. Let's see here. Of 0.66, or that actually, Yeah, okay. So in this case here, basically kind of, it doesn't really tell you that you have to get that exact number, but potentially this is actually where you'd end up losing the mark because we are not within our range. And then it says provide pertinent reasoning. Yes, to use graph 2 to determine the wavelength of light. So you're actually using graph 2, you can actually show it on the graph like that, right? Kind of basically showing some details along here. So this is your reasoning, flipping things around and following along, and arrives at a correct value. So in this case here, basically there is what we call follow-through marks allowed, right? And that means basically if you made a big mistake up here, and say I use my original number for 1.506, which is way down here, and made a stab at the dark saying, all right, well, if my graph is curving, that'll be about maybe 750, and I gave my number as 750 and everything else was correct, I could potentially get some follow-through marks and have 3 marks for this question. I hope that helps. This is essentially what our Prac 16.1 that we just did. This is the type of working out you're going to be doing in that Prac, except you've now got a data table, which should help as well. Any other questions? Shoot me an email.